Hi everyone, this is Sai Teja. Today my TikTok topic is about least squares estimation. Today I am going to explain about the least squares estimation. Let's go into our topic. In this topic, we are going to learn about what is the least square method and also least square methods types and also solving the least squares by using the formulas. And also we can see the some other different like linear least squares, non-linear least squares, linear regressive, non-linear least squares, etc. We can see. Let's go into our topic. Introduction. The method of least squares is about estimating parameters by minimizing the squared distances between observed data on the one hand and their expected values on the other. We will study the method in the context of a regression problem where the variation in one variable called the response variable y can be partially explained by the variation in the other variables called variables x. What is the least square method? We are going to know what is the least square method and how it will be used in solving the problems. First of all, now we are learning about the what is the least square methods. The least square methods is the form of mathematical regression analysis used to determine the line of best fit for a set of data, providing a visual demonstration of the relationship between the data points. Each point of data represents the relationship between a known independent variable and a unknown dependent variable. In this, we are going to learn about the given data provided by the visual demonstration. We are going to know about the relationship between the data points. In that, we are knowing about the independent variable and the dependent variables. Least squares. The method of least squares is the standard approach regression analysis to approximate the solution of overdetermined systems by minimizing the sum of squares of the residuals made in the result of each individual equation. The result of fitting a set of data points with a quadratic function. You can see the diagram how the quadratic function we have set into a data points by the using of the least squares. Here we can see the graph from -2 to +2 on the x-axis, and we can see the 0 to 3 on the y-axis. We can see observing the graph how it will be slowly increasing. The red dots indicate the how many times it was repeated, and the blue ray it will show the distance from how it will be increasing by using these least squares. The most important application is in data fitting when the problem sustain uncertainties in the independent variable, then simple regression and the least squares method have problems. In such cases, the methodology required for fitting errors in various models may be considering instead of that for least squares. And also conical fitting a set of points using least squares approximation. We can see the diagram how the conical fitting of a set of points was inserted in the least squares. We can see the diagram and we are indicating the points with x, and also we can see the x-axis with the a indication and y-axis with b indication. These are the sum of examples for the least squares. And also with the least squares, we can calculate the so many problems we can see on the later. The nonlinear problem is usually solved by iterative refinement. At each iterative, the system is approximated by a linear one, and thus the core calculation is similar in both cases. Polynomial least squares describes the variance in the prediction of a dependent variable as a function of independent variable and the deviations from the fitted curve. In this, we can know the nonlinear problem is usually solved by the iterative refinement, which means nonlinear problems also can be solved by the using this function. And also we can see the independent variable and the deviations from the fitting curve. Previous diagram, we can see how the independent variables and deviations form the fitting curve into a oval shape. Let's go into problem statement. The objective consists of adjusting the parameters of a model function to best fit a data set. A sample data set consists in a dependent variable whose value is found by observation. The model function has the form of f of x comma beta, where m adjustable parameters are held in the vector beta. In this problem statement, we are consisting of adjusting parameters. A simple data is a dependent variable whose value is found by the f of x comma beta, where m adjustable parameter are held in the vector beta. We can see the solution. The fitting of a model to a data point is measured by its residue, defined as the difference between the observed value of the dependent variable and the value predicted by the model. And we can see the formula which we use it to calculate this. R of I equal to y of I minus f of x of I comma beta. We can see the graph. We can take in the values from an x-axis. We can take in 1 unit is equal to 0.15 centimeter. And also on the y-axis, we have taken 1 unit is equal to 1 centimeter. And here all the some dots which can indicate the diagram and showing the dependent variables on the value predicted by the model graph. We can observe the graph through the diagram on the screen. The least squares method finds the optimal parameter values by minimizing the sum of squared residuals. We can see a sum of squared residuals S equal to summation I equal to 1 to n r square of I. If this is the one type of formula for the minimizing the sum of squared residuals. By using the least square method. We can see this. An example of a model in 2 dimensions is that of the straight line, denoting the y-intercept as b0 and the slope as the model function is given by f of x comma beta, that is equal to beta naught plus beta 1 x. This is one type of formula for the least square. By minimizing the sum of squares, we can see through the diagram. Solving the least squares problem. We can see before that we can see the derivation and also the formula. Now we are going to use that formula and we are going to solve the least squares problems. Let's see how we are going to solve and how it will be going through further. The minimum of the sum of squares is found by setting the gradient to 0. Since the model contains m parameters, there are m gradient equations. We can see the formula dou of s by dou of beta j equal to 2 summation of I, r of I equal to dou ri by dou beta j, that is equal to 0. J values we can take 1 to so on, and also we can use the formula before we are shown in the screen. We can use by using these two formulas, we can solve the least squares problems at containing m parameters. There are some m gradient equations also. We can use these both formulas and we can solve the least square problems. The gradient equations apply to all least square problems. Each particular problem requires particular expressions for the model and its partial derivations. We can see the formula, how it was derived from the before we are shown and how it was derived by the graduate equations applying to all least square problems. With the help of graduate equations, we can solve the derivation formula uh, into a partial derivatives. We can see through the monitor. Next, linear least squares. A regression model is a linear one when the model comprises a linear combination of the parameters. That is, f of x comma beta equal to summation j to 1 of m. We can see the formula of linear least square parameters, and with this we can solve the regression model in a linear where the function pi of j is a function of x. In this formula, we have taken the pi of j. It is the function of x variable. Letting xij equal to pi of j into x of y, and putting the independent and dependent variables in matrices x and y respectively. We can compute the least squares in the following way. Note that D is the set of all data. In that given formula, we have taken the D is the set of all data. We can see the formula L of D comma beta. We have taken the set of all data into a variable called D, and we can observe the variables, dependent and independent variables in a matrix X and Y. We can see the formula, how it was derived. Finding the minimum can be achieved through setting the gradient of the loss to 0 and solving for beta. We can see how the minimum can achieved through setting a gradient of loss to 0. Before that, we got the derivation, and we furtherly divided as changed into the gradient form, and now it was turned into a beta of equal to x power t into x of inverse into x transpose of y. We can see the formula how it was derived and formed into a beta form. Non-linear least squares. There is in some cases a closed form solution to a non-linear least square problems, but in general there is not. In the case of non-closed form solutions, numerical algorithms are used to find the value of parameters beta, such as then the parameters are uh, defined that is the values are obtained by successive approximation. So we can see in the non-linear least squares there is in some cases a closed form solutions are called non-linear least square problems, such as closed form solutions called numerical algorithms used to finding the value of parameter beta. In that, we are uh, using a formula beta of j power k plus 1 equal to beta of j power k plus delta of beta j. We can use this formula by solving, and we can find the value of parameters such as beta in the closed form solution called numerical algorithms. Through this, we can find the non-linear least squares, and we can solve the equations. Where a superscript k is an iterative number and the vector of the increments delta bj is called the shift vector. In some commonly used algorithms at each iteration, the model may be linearized by approximation to first order Taylor series. In this, we can see the delta bj is called the shift vector, and some commonly used as algorithms model may be linearized by approximation to the first order Taylor series. We can see the formula f of x of I comma beta. We can see how it was derived by using the first order Taylor series. We can see on the screen. Linear regression. Consider a case where f of beta is a linear function of beta. That is, f of beta of x equal to x1 of beta 1 plus x2 of beta 2 plus up to xp of beta p. So on here, x1 to xp stands for the observed variables used in the f of b of x. We have taken the values x1, x2, so on up to xp. In case of f of b of x, it stands for the observing variables used in the f of b of x in the linear regression. The variance of the least squares estimator in order to construct the coincidence intervals for the components. The variance of the least squares estimator in order to construct the confidence intervals for the components of beta are linear combinations of these components. One needed as the estimator of the convergence, the project of the vector y on the plane spanned by x. We can see the diagram how it was projected from the vector y on the screen and how it will be if we have taken the axis of y up to angle on the x vector. We can see through it. The variance of the least squares estimator in order to construct the confidence intervals for the components of beta are linear combinations of these components. One needs as estimator of the convergence. We can see the diagram how it was drawn by using the least square estimator, uh, constructing the convergence intervals for the components of beta. And also, we can see the estimator of the convergence. The projection of the vector y on the plane spanned by x. We can see how the x and y are spanned through the x-axis. Now we are going to learn about nonlinear regression. When f of b beta is a nonlinear function of beta, one usually needs iterative algorithms to find the least squares estimator. The variance can be approximate as in the linear case with f of beta of xi taking the role of the rows of x. Here f of beta equal to delta of f of beta into x of I by delta of beta is the row vector of derivatives of f of beta into xi. We can see the nonlinear regression with the help of this. We can how we are derivating the formula into a vector form by solving the row vector form. Now we are going to testing the linear hypothesis. The testing problem considered in the numerical example is a special case for testing a linear hypothesis. We can see a of beta equal to 0, where A is a some R into P matrix, and another example of such hypothesis. Suppose we want to test whether two coefficients are equal, say H0 beta 1 equal to beta 2. This means there is one restriction, that is R1 equal to 1, and we can take A as the 1 into P row vector. A equal to, we have taken positive and negative values from negative to positive. In between, we are taking included 0 also. Thank you all.